So, as with linear methods, we will first start by looking at regression, right. So, we will see how to use decision trees for doing regression. So far I have just told you how to do the partitioning, right. So, let us look at regression trees. Okay. So, I split the region into 4, right. So, I will first see if the data point that comes to me, right, whether it lies in region 1 or region 2 or region 3 or region 4, and for each of those regions I am going to have some constant that I will output, right. So, if you think about it, the function that I will output from here, right. So, we will have one value in this region, right, one value in this region, right, another value in this region, another value in this region. So, it will be like a piecewise constant thing, right. So, people understand that, right, you are not going to test my 3D drawing skills, right. So, you can see that there will be one output for any point in this region, one output for any point in this region, one output for any point in this region, one output for any point. In this sense, in some sense it is similar to KNNs, because you are assuming that there is a piecewise constant assumption about the function that we are trying to model, right. By the way, is the KNN parametric or non-parametric? Parametric, okay. What are the parameters? So, is it parametric since it depends on n? As n becomes larger, what happens? So, I can apply one of those ideas here. Instead of fitting a piecewise constant per region, you can fit a linear function on that region, right. I have done the splitting, right. So, I am going to have some training data, right. So, some of the training data points will be here, some will fall here, some will fall here and some will fall here. I can take all the points in R1 and fit a plane to that, right. I can take all the points in R2 and fit a plane to that, likewise for R3 and R4, right. Will that be better or worse than fitting a constant? Better. No, actually it does not depend, actually it is always better, right. It is always better. In the worst case you will fit a constant. I mean, if constant is going to be really better, you will fit a constant because you are minimizing squared error, you will anyway end up doing that, right. So, what is the problem with that? Huh? You have to do more work, yeah, you have to do more work, and there is variance, a significant variance. We will come to the variance bit, yeah, but the significant variance. But such things are called model trees sometimes. Model trees. In fact, you can do more complex stuff itself, right? It does not have to be linear. A linear is easy, right? I can do any kind of regression I want on this, right? I can fit, I can use a neural network if I want, and to learn a curve only on the data points that lie in R1, right? Not a good idea usually because I have already divided my entire training data into at least 1/4 if not smaller, right. I mean, some of the regions could have much smaller data, some could have more, right, but still I am cutting down on my training set that is available. So, it is going to be harder to train, right. Okay. So, I am going to erase this stuff and try and generalize this, or let me do it again, okay. So I have n observations, as you all know. Right. So that is our usual setting. So where the input comes from RP and the output comes from okay. Right. So the function that we are trying to learn is Cm and Rm, right. So the set of parameters that we have to estimate are Cm and Rm, correct. So we need to know where are we splitting, how are we splitting the region, and having found the regions, right, what is the constant that will fit within that region, okay. So there are the two questions: determine the M regions and given the regions find the response, right. But one thing to note is, unlike K and N or anything, the M is not given to you, right. M is something that you discover from the data, and that is why I said it is non-parametric, right. You can actually have more regions if the data requires it, you can have lesser regions. M is not given to you a priori, right. But sometimes as a regularizer you can decide to fix M as well. You can say I do not want a tree that is more than 4 levels deep, right, as a complex T measure, but again that is derived from the problem definition. The model itself is not parametric, right. So let us look at the second question first, because that is easier. We actually have a proper answer to the second question, right. Right. So this is essentially what we are trying to minimize, right, and so we can try to do this region wise, right, because the output that I produce for one region does not depend on the output I produce for another region. So I can do this minimization region wise, right. So I can pick, yeah.
So won't this give an overfitting model, like every point would have its own box, kind of that?
Great. Yes, could likely.
Then that would be kind of mapping everywhere.
Exactly. So we will come to that. We will again address this question later, right. Yes. So assuming that there is some amount of, so you will not, okay, let's step back and do this. You are going to get training data. At best what you would do is, you would have regions such that within a region only one point sits, right. So that is not saying that I am going to fit it tightly around that point, right. So whole of R4 there might be only one point, but still there will be some kind of regional segmentation that is happening on the input data, right. Second, I am going to introduce some kind of regularization that prevents me from doing that. Okay, so that we'll have to be very careful.
Situation where the number of regions is basically the number of training data that you're given.
That's exactly what he was asking. So you could end up with that. That's what I'm saying, and you have to find some way of regularizing it so that you don't do that, right? Right. So if you're going to minimize this region wise, but anyway, right now I'm talking about given a region, right? So that's easy. So we will not be overfitting things. So given the region, right? So I am going to find out what should be the output of the mth region, right? Cm is the output of the mth region, right? That is what we assume. What should it be?
Transpose x whole inverse. Transpose x whole inverse.
Give me a simpler. I am fitting a constant. I am not fitting a straight line here. Average of all the points. Okay. Like average of all the points which lie in the region, and take the yi's corresponding to the points lying in the region and take the average. Okay, that's the best response. That's easy. Okay, that's done. What's the harder part? Finding the regions, right? In fact, it can be shown that finding the best possible RM, set of RM, right, is actually NP complete, right? Huh? It's NP complete. No, yes, NP is actually NP complete, right? So you can show that finding the best possible RM is very, very hard, right? So we have to come up with some kind of approximation. So essentially, we use a greedy approximation.
The training data, they are not specifying which region it belongs to, then what is the output of the.
No, they just tell you what xi. I told you what the training data is, right? Yeah, this is all the training data is. You get xi, yi.
Your job is to cluster.
Your job is to find the regions and find the response.
So,
Yeah.
what is exactly NP hard to map all those to find all
See,
the best such regions?
Yeah, find the best region. I mean, you can, given a region, you can tell me what the performance is, right? But then finding what the best such segmentation is actually hard. You have to search through the combinatorially many segmentations. So the way we do it is following, right? Yeah.
So wouldn't 1 point per region would be the best?
What's that?
1 point per region. Wouldn't that be?
You can have only some.
No, for a given m, I want to find the smallest m such that I get that performance.
Smallest region.
Smallest region set, yeah. The smallest region set for which I get the performance. That's really ideally what I'm looking for, right?
Smallest m.
Smallest m.
Not even to reduce m.
Sorry?
Given an m, you have to find the region.
Given an m, finding the region, yeah, in general that is also hard, but I want to find it for the smallest m as well. Right? Ideally, you want to find it for the smallest.
So as in like there's some trade-off here, right? Like you would have to either specify the m and then you find the best, or you say that you find the best and find the smallest m for which you can do that.
Ideally, it should be find the best and then find the smallest m for which you can do the best, right? But we end up doing compromise on that as well. So what we will do is, you guys are making me go do this all out of order by asking leading questions. But what we are going to end up doing is we are going to say, okay, here is a greedy algorithm, right, greedy algorithm, find the best that the greedy algorithm can do, okay. Now find a smaller tree, okay, that will achieve close to the greedy algorithm's best performance. Again I will have to make a compromise there, I can't say that give me the smallest tree that will give me the same performance as the greedy algorithm, because if that exists one, in fact greedy algorithm would have found it, right, along the way as it was growing, right, and therefore we will have to say that okay, give me a smaller tree, right, that is close in performance to what I get with the greedy algorithm, right. See, remember we already made an approximation by assuming we are doing recursive partitioning, right. So you can't get the best possible performance, okay, that we have given up, right, by choosing a tree representation, right. So this does a lot of approximation, that is why I said, right, I mean there is no good understanding of how decision trees eventually work. If you ask me two specific questions like okay, how good an approximation will this greedy algorithm converge to, right. Suppose my performance, the best possible performance on this, like the Bayesian optimal error on this data set is say 93% performance, I can say 7% is optimal error, okay. How close to optimal error will a decision tree algorithm get to? No answer, right. While you can answer some of those questions for things like logistic regression and consider some splitting variable j, okay. So what I mean by a splitting variable, the splitting variable is the question that I ask here, okay, this variable here in the question, so x1, right, or x2. So in this case the splitting variable is x1, here the splitting variable is x2, okay, and what is the split point? It is the number on the other side, right, so 0.6. So in this case the splitting variable was x1 and the split point was 0.6, okay, right. Consider some splitting variable j and a split point s, okay. Okay. So I am splitting my input data into two parts, one where the jth variable is less than s, less than or equal to s, the second part where the jth variable is greater than s, okay. So I am splitting it into two parts. So what we really want are j and s such that so I am seeking j and s such that if I fit the best value for the points that lie in R1 and if I fit the best value for the points that lie in R2, that is what the inner minimization is, right. So sum of this is minimized, so sum of the squared errors over the two regions is minimized, right. So the j and s actually influence which data point goes to R1, which data point goes to R2, right. So once I decide which points go to R1 and R2, I have a fixed optimization problem that I solve, right, which is one we already solved there. Yeah.
Aren't you missing out on the previous, like we are splitting the whole thing?
Wait, I am just talking with the full data set, right, I am at the root, right, then we can worry about the recursive splitting part, right. right. So make sense for people so far? Yes, I want to find J and S such that this happens, right. How do you solve this minimization problem? We can do this, huh?
Isn't this kind of classification?
No. This is not classification, right? This is actually regression I am solving, right. So, for all these data points in R1 I am going to output one value, for all the data points in R2 I am going to output another value. So, you can think of saying that okay I am grouping all R1 into 1, I am going to output one value, I am grouping R2 into 1, I am going to output one value. Find the right grouping such that I can output a value such that the overall error is minimized. Okay. So, the first thing no it can be slightly better than that, right, or worse I do not know, I will tell you, it depends whether you are better or not. Okay. The first thing you have to note here is I am going to do this for each and every j that I have, okay, find the s and then I am going to pick the best j, right. I am going to do this in turn for j equal to 1, j equal to 2, j equal to 3, from 1 to p I am going to do this and then find the best s, and that will give me a value for the objective function, right, and I can use this to compare which j is better, right. So I do not have to do this jointly, okay. So that is the first thing you have to notice, okay. So given a j, right, how will you find the right s? So once I have fixed a j, you can think of it as just a line, right. I have to find a s at some point so that I can split everything to one side to R1, everything to the other side to R2.
You could keep choosing some steps for S. And
exactly. So what are the steps I should choose for S? So he was talking about recursive doubling, that is one way of doing it if you have no other clue, right, and then you have to come back and then you have to search through the, so people know about recursive doubling. I start off by looking at 2, then 4, then 8, right, I keep doing that. At some point the sign will change, right. So I mean I will be fitting it one way, then I will actually my error will start increasing again. So I stop and then now I will have a window of some power of 2, right. So I have to look between 8 and 16 and then I will do a search through that. That is one way of doing it, but there is a slightly better way we can do it. Any guesses?
what if you just pick some reasonably small fraction?
Something better than that. Imagine you are trying to do this, not imagine, remember that you are trying to do this from data. I have given you a training data set. Huh?
Whatever coordinates for the training data are there.
Exactly. So order the training data along ascending order in that coordinate, right, and then just keep hopping on that. Right. Suppose I have data here, here, here and here, somewhere there, right. So now if you think about the x2, let us say x2 is my or x1 is my splitting criterion. So there are only 5 different values of x1 that actually occur in my training data, right. So there is x1 equal to this, x1 equal to this, x1 equal to this, this and this, right. It does not matter if I consider any other values for x1, because there is one of these 5 values will give me the same split, right. Suppose I consider this as my splitting point, does not matter, I could have as well considered that as my splitting point. You see that, right. So I do not have to consider, I do not have to go smoothly along x1, I can just use any one of the data points that has come to me already, right. So that is the easy way of searching for the splitting point in x1, essentially what we will do.
So if x1 equals 0.6, what will happen? What region will you keep it?
Right. So just add it to one of the regions. I already used a less than or equal to here. Just notice that. Right. So how much work do we have to do for finding one splitting point? n cross
n log n.
n log n. Oh, because of the sorting part, is it? Okay.
So
Yeah, you don't have to sort. Yeah.
have to actually sort it, right?
Yeah, you don't have to sort. That's what. Yeah, you can get away. Yeah, you can just go through whatever order you get. Yeah, it doesn't have to sort. Yeah. Huh?
Like the unbalanced, you keep on.
No, if you sort, I mean, the computation becomes a lot easier. But for computing the complexity, you don't have to sort, right? You can leave it as it is. You can. It's NP. N for each feature, and you have P features, right? So the amount of work you have to do is NP. But if you sort, then life is a little easier. But you don't have to. When you're writing the code, you will know what I mean. Yeah, NP is the amount of work you have to do for one feature, one level, right? Great. So now what we do? I have found the optimal J and optimal S. Have I? Yeah, optimal under all our assumptions, right? Because I am actually doing an exhaustive search over J and S, right? I am not doing any approximation here. I am doing an exhaustive search. So given the assumption that we are going to do something greedy and we are going to split on one variable at a time, so we are finding the best possible variables. Great. Now what do? I actually create the two sets R1 and R2. Right? Having found the best possible splitting point and the splitting variable and the splitting value, I find the two regions R1 and R2, and then I go into R1, I do the whole thing again, assuming that R1 is my entire data set. Likewise, I go into R2 and I do the whole thing again, assuming R2 is my entire data set, right. Does it make sense to consider the J again, the J that you split on, say some J star, right? Does it make sense to consider J star again? Yes. What does not make sense is to consider J star along with the same S. In fact, it does not make sense to consider J star along with any S greater or lesser depending on which side you are, right. So you can progressively you keep pruning your search space down, right, but you do not have to worry about it because it is automatically taken care of, because you are only looking at the values that are present in your data point. I have not written those things down, right. Do you want me to write down the whole process? All of you remember it, right? Oh, J star is the one that gives me the minimum in this, right. I am considering each feature in turn, right. So J star is the feature that I finally choose to split on, and S star is the value that I finally choose to split that J star on. Okay, there is another question somewhere. Okay, good. Okay, great. So how far do we go? So this is the question that we all had in our mind from the beginning, right. If I do not put any restrictions on it, I will keep going until I have one data point per region, right.
Till the number of features at least.
Maybe you have a number of levels.
Great, yeah. So so that is a very other people actually notice it. It could very well be that the number of features ends, right. How can you, yeah, J can be repeated, but if J can't be repeated, can you end up with something like this, where there is only one data point per leaf, per region, or where there is no, sorry, there is more than one data point per region.
Maybe you can fix the number of regions altogether.
Yeah, you could do that, but answer my question. We are allowing features to be repeated, right. Can you still end up with a point where you can't grow the tree anymore, but you have more than one data point per region?
If you keep getting your best splitting point as your border of your region, then you can't recurse any further.
No.
So y value for both points. Is the y value for both the points in that region is
Not
same?
they are the same data point. You can repeat it. I never said your xi's have to be unique, right. No, it's not. It sounds like a trivial thing, but no, it's actually important. I mean, you should think about it, right. So this is very important in cases where the yi's are different, the xi's are same, and the yi's are different. There is no way you will get 100% correct.
Isn't that noise?
Maybe.
Because for same value.
Maybe.
If you have
if you are assuming that it is a deterministic process, truly underlying process is deterministic and it is corrupted by noise, yes. But what if it is a stochastic process, truly a stochastic process that is generating all of these things for you, right?
Be allowing redundant case.
Yeah, sure, you can. You should. There is no question of you allowing it. It's life happens to you. Yeah. Yeah.